So today we begin a brand new topic, which is the second one. And more precisely, this is about radiative transfer. You see all the different topics that are part of what we will see during the next classes, because this is going to take us more than just one class. And so a lot of topics, but essentially, just to give you an introduction of what radiative transfer is, well, studying radiative transfer means you are interested in understanding how a field of radiation, a radiation field, is affected by matter. So just imagine some gas which is filling up a region of space, and you have radiation crossing the space. So you wonder how this radiation field is affected by matter. And you can immediately figure out that matter can affect radiation fields in both ways. Both it can contribute to produce further radiation, but it can also absorb it. So as a matter of fact, when some radiation field crosses some region which is filled up with gas, with matter in general, you expect some kind of interaction, so some kind of modifications of the radiation field due to the matter itself. So essentially, radiative transfer deals exactly with this kind of problem. Study how the radiation field is affected by matter. So how radiation is transferred throughout some medium. Okay. And as I told you, this essentially concerns both processes, the ability of matter to absorb radiation as well as the ability to produce radiation. And we will see how this is encoded in the equations that we will see. The quantity that we need to use to describe the radiation field properties is something that we already encountered in the previous lecture. It is so-called intensity, or specific intensity, or just brightness. So how it is defined? Well, the quantity I'm talking about is usually denoted with I, nu in the sense of specific, so depending also on frequency. So, well, just look at here at the energy, at the unit of measures of the intensity. It's energy per unit area, per unit frequency, per unit time, per unit steradians. This is in the GZS system. So what does this mean? Well, just think of a surface element that we call dA. You've got some radiation crossing this element, and in particular crossing within a time interval and directed along within some given solid angle. So we define the specific intensity as the amount of energy over the area crossed by this energy in a direction which is perpendicular to the area itself. Okay, so the direction here is not by chance, which is drawn perpendicularly. This is just on purpose. So the amount of radiation crossing a given surface area per unit time, per unit frequency. What does this mean? It means that I only consider photons having frequency between nu and nu plus the nu, and moving within the solid angle d omega. So if I want to express the energy dE, I have to multiply by definition of a specific intensity I nu by the area dA, by the frequency interval d nu, by the time interval dt, and within the solid angle d omega. So just for, if you look at the units of measure, by multiplying by these four terms, you see that we recover Earth's energy. So this is very important. So I is the main quantity that we will be continuously referring to express, to characterize the properties of the radiation field. Once you know I, you know everything. Mind that I, not only is I a function of direction, but it's first of all, it's a function of the point in space. You change point in the space, and I may change. So radiative transfer aims to study how I nu depends on the points in space, as well as on frequency, on direction. So all these is encoded into this quantity we call I, we call specific intensity. So the goal is to know as much as possible I. Once you know this function, essentially you have all the information required to characterize your radiation field, okay? We will be defining a few quantities in the next minutes. So I'm just trying to go not too fast. There is also another quantity, which is a scalar quantity. I is a scalar function, okay? I didn't say that, but that's. So we can define, once you define I in one point in space, in that point, you can imagine to have a given element surface. Again, dA. But dA is an element surface who's also characterized by the direction of the surface. And the direction in this case is defined by the unity vector NA, okay, which is understandably, which is perpendicular to the surface itself. So you have the surface with a given direction. So you can define the so-called net flux, which we call F nu, as a function of the orientation of the surface element, which by definition is just the specific intensity integrated over the entire sky. So it's an integration of the solid angle. Mind that times cos theta, where theta is the angle between the generic direction which you are integrating and the fixed direction which is given by the orientation of the surface element. So that's why it's a function of the surface element, because you change orientation, and as a consequence, by definition, the net flux can change. Okay, so you see that because of the cos theta properties, it means that it somehow weighs in a different way with a different sign the radiation coming from one side of the surface to the other, from the radiation going through the opposite direction, because the cos theta changes sign. To let you understand, to let you appreciate better this point, let's consider the easiest case possible you can think of a specific intensity, the so-called isotropic case, the case in which I doesn't depend on the direction, okay? So in that case, what is the net flux? Well, it means that I nu is constant, doesn't depend on the direction. So if you integrate something over the solid angle, something which is constant, of course you can take it out of the integral. You have the integral of cos theta integrated over the entire sky, that's 0. So what does this mean? That in the case of an isotropic radiation field, the net flux crossing a given surface is 0. Net flux. Why? Because if the isotropic field is completely isotropic, this is also easy to understand. Why? Because if it is completely isotropic, you have a surface, it means that you've got an amount of radiation which is going from one side of the surface to the other side, and the same amount of radiation you have in the opposite direction, because of isotropic, because of isotropy of the field. So the net gain, you have no net transfer from one side to the other of energy carried forward by radiation. You have got as much energy going from one side to the other and in the other way around. So the net result is 0. So this, while instead, if you have just, let's suppose, for example, I nu, when it is parallel or close to parallel to NA, is positive, and in the other case, you have 0. For example, if you consider as a surface element just the surface element of the surface of a star, in that case, you have just radiation coming out just in one direction. If you take the opposite direction, you've got nothing, because you are considering the direction from the vacuum to the star, nothing. So in that case, the net flux is positive when you consider a surface whose unity vector is going outward, not inward. Okay. Having defined the net flux, or better, the specific net flux, again, whenever you've got something specific, you can define the corresponding volumetric quantity. And I remind you, volumetric means that you are integrated over frequency. So much in the same way as we define the specific net flux, you can define the volumetric net flux, in which what you do in addition is just to integrate over frequency. So you see, I just took the specific net flux, F nu here, and just I integrate it over the electromagnetic spectrum. So integral over dν, and this is just the volumetric net flux, which still depends on the direction of the surface, so on the orientation of the surface, okay? You rotate the surface element you are considering, and as a consequence, the flux and both the specific flux and the volumetric flux can change in principle. That's why I explicitly wrote the dependence of the flux and both kind of fluxes on the direction, on the orientation of the surface. Units of measure for the flux density, so F nu, not the volumetric one, the specific one, there's a specific units of measure which come from, well, I'll tell you later. It's called Jansky, and it is denoted with JY, capital JY. One Jansky is 10 to minus 26 watt per square meter per hertz. So let's consider the units of measure to make sure that this is really flux density as we would expect from definition. Well, watt is just power, so energy over time, over surface, meter squared, over frequency, Hertz minus 1. So energy per unit time, per unit area, per unit frequency. What is missing is per unit steradian, per unit solid angle, but we integrate it. If you look at the definition of flux, that's exactly I integrated over, so that's okay. And if you want to express in the CGS system, this is 10 to minus 23 ergs per second square centimeter per hertz. Why do we use this? Well, in what kind of context? This is a typical unit which is adopted in astronomy. So this is typical of astronomy. And the reason, the historical reason for this unit, and also for the magnitude, you see 10 to minus 26 is something which is really small compared to the units of measure of the international system, as well as the other. But the reason is why, well, Jansky, who was Jansky? Jansky was Karl Jansky. He was both a physicist and an engineer, radio engineer. He lived kind of 1 century ago. And essentially, he was just an engineer and just dealing with, he was employed, I guess, by the Bell Laboratories at the time in the US. He was just trying to figure out what kind of antenna would work better in some context, and he realized that there were some radio signal from the sky, from the galaxy. So essentially, he's the guy who just gave birth to radio astronomy. And so people just wanted to give the units of measure to him, after him. And there's also a very important radio telescope in the New Mexico, which is the Very Large Array, which is also bears his name. So anyway, okay. So let's having introduced so many quantities, let's have an example, practical example of a calculation of flux density. So very, very simple kind of exercise. So a radio telescope with a collecting area of 1.2 meters squared observes a radio source at a frequency of 1420.4 megahertz with a bandwidth, so delta nu, bandwidth of 2 megahertz, measuring a detective power of 1.2 times 10 to minus 19 watt. What is the flux density of the source of the discovered frequency, observed frequency? Sorry. Well, easy. You've got the power, so essentially you've got the area. Just think of the units of measure. I usually, sometimes when I just think of the units of measure. So in this case, you want to know the flux density. Remember, the flux density is power, it's energy over time, over surface, over frequency, and that's it. So you've got power, energy over time, you've got the surface of the radio telescope, you've got the bandwidth. Mind that here you've got two frequencies. The central frequency, the center of the frequency interval, and the width. Here what you need is the width, the frequency interval. So the interval within the electromagnetic spectrum in which this power is released. So just replacing the values, in this case the calculations were made in the international system, just to let you be. So easy, 510 to minus 26. Make sure when you've got these quantities, make sure you are in control of the units of measure. That's why I wrote them explicitly. That's important because it's easy to make confusion, to lose some of them, or just to add some something which is not required. So what the square? Well, the numbers is easy to calculate. Watt per square meter per hertz, which is exactly what I would expect for a flux, for a specific flux unit. Okay, so also makes sense from, which is exactly, if you remember the definition of Jansky, this is exactly 5 Jansky. Yes, this is a remark that I already made, so this is important. I just wanted to put both frequency value because just to make sure that you are not confused by which is to be used. In this case, it's a frequency interval. I don't care about, in this case, I don't care about the central frequency, which is 1.4 gigahertz or 1,000 and 1,400 megahertz, whatever, which is, by the way, has an important meaning in astronomy, but I'm not going to comment on this. Okay, let's move on. Having defined the specific flux and the volumetric flux, I can define two corresponding quantities. One is the specific luminosity. What is that? Well, it's the integral of the specific flux, integral over the surface, over the emitting surface. So again, if you remember, the specific flux was energy per unit time, frequency, area. I'm integrating over an area, so the specific luminosity is just supposed to be ergs, energy, per unit time, per unit frequency. That's it. And indeed, just because by integrating onto a surface, onto the emitting surface, you just got rid of the per unit area. So you're just left with ergs per second per hertz. And in general, in astrophysics, luminosity, whenever, do not make confusion between luminosity and brightness. Brightness is the guy we met just in the previous slide. Luminosity and depends on several things. Luminosity is an intrinsic quantity of the astrophysical object that you are considering, and it's just erg per second, luminosity. Here we have specific luminosity. So ergs per second per hertz, because the word specific means per unit frequency or per frequency interval. So in a completely symmetric way, you can define the volumetric luminosity by integrated over the frequency, the specific luminosity. So again, if you look at the units of measure, you by integrated along frequency, you get rid of hertz at the denominator. So you're just left with erg per second, which is exactly what I was telling you. So it's a power. Luminosity, it's a power, which is how much energy a given object is emitting per unit time. Just like that, luminosity. You can just say luminosity. As I told you, when nothing is specified, it's meant to be volumetric, okay? So either volumetric luminosity or just luminosity, that's the same quantity. We can define another mathematical object, which is now a vector. And this is called radiative flux field, defined that way. So let's have a look more in detail at the definition. So you have two integrals. The first, which appears here, is an integral over frequency. So that's why you don't see in the name any word like specific. This is not specific because you already integrated along over frequency. Let's have a look more in detail at the second term. So you see, the intensity, I knew, in which here I explicitly wrote the dependence on both the point in space, so R, you change point in space, and I may change, but also on the direction. You fix the point in space, you change direction of what? Of the surface you have in mind. I'm talking about flux. So flux, talking about flux means that you have a surface that you want to see how much radiation is crossing that surface. So you change orientation of the surface, you change n, unity vector n. And you see, this is weighted by n itself. So it's a vector in which you integrate over all the frequencies and you sum up all the unity vectors corresponding to all. But each of the unity vector you sum up is weighted by the corresponding intensity. So if you think of a field, for example, or of a field in which intensity is much stronger, much higher in one direction with respect to the other one, of course, the resulting sum, vectorial sum, would be directed along the direction in which you have the strongest flux. So the idea is that. So it's a vector, because it's a sum of vector. While it might look like something not very easy to manage, well, it's useful because now we can think of we can rethink of the flux and the luminosity coming out of a given element of surface, flux and luminosity. If we define, for example, an elementary vector, which is just the surface element times NA, so the unity vector of that surface element. So we can now we are going to prove that the contribution, the elementary contribution to luminosity coming out of a given element surface, I can see it as the scalar product between the newly defined radiative flux vector and the vector, the elementary vector of the surface area that I'm thinking of. Why this? Well, just do the calculation. You take the definition of radiative flux and you just replace dA, defined in that way. So you immediately see that, well, NA is fixed, while N changes because you are integrated over the entire sky. So N is a variable. You cannot take N out of the integral. But you can bring NA, which is the direction of the element surface, which is fixed. So you can just bring inside the integral, no problem. And so this is exactly what I did here. I just emphasized that the scalar product is between these two unity vectors, of which this is fixed and this is a function of the solid angle. But this is a scalar product between two unity vectors. So it's just the cosine of the angle between the two vectors. This is theta. If you have in mind, again, this drawing, you see, you are integrated over the entire sky, so theta changes, but theta is the angle between the fixed direction given by the orientation of the surface and the generic direction. So that's exactly what we call theta. But if you remember the definition of specific flux, and which is exactly what I wrote here on the bottom left of this figure, this slide, you see that we defined the specific flux as a scalar in that way. So I weighted by the cosine of theta. And cosine theta means you have a given fixed direction in mind, which is exactly the direction of the element, of the surface element. So you see that you recognize this guy, I. Now you have no more scale, no more vectors, you see. You had just one That's exactly what we expect. This is a scalar product, so in the end, the result must be a scalar. So I weighted by cos theta, integrated over d omega. This is exactly our specific flux. This is just like that. Then we have also, finally, we have the integral over frequency. That's the flux. No more specific, just flux. And flux times dA. So flux is energy per unit area per unit time times dA, which is an area, so energy per unit time. dL, which is exactly what luminosity is supposed to be, energy per unit time. Okay? So another way to express, in this case, what is dL? dL is the energy per unit time coming out in that direction that I showed you before, here. So dL is just how much energy is crossing this way, per unit time, this surface element. Mind that it could also be negative. If it is negative, it means that the net flux is in the opposite direction with respect to the direction of the surface element, okay? So the sign here has a meaning. It's not, even if you think of a positive quantity, but in this case, if it is negative, it means that just energy is flowing in the opposite direction with respect to the direction NA. Okay. In principle, in some cases, maybe you don't know. So the sign is telling you this piece of information. Okay, so again, let's make an example just to make sure that we are in control of things. Very simple example. So let's consider an isotropic source. So the same this source, which I showed here with a yellow color, is an isotropic source. What does this mean? Well, it is just emitting radiation in the same amount toward all directions, okay, the same amount. So no preferred directions. Let's consider, we calculate now the flux and the contribution to luminosity as measured in two different points. Point 1, so we ideally put a surface element, which I call dA1, at a distance R1. And the orientation of this surface element is just, let's imagine this surface element lies on the spherical surface at that distance. Okay, so it's just a small tile of the surface with radius R1. Then we will play the same game considering another sphere on radius R2. But let's just focus on point 1. So we wonder, what's the amount of energy per unit time coming out of this element, of this surface element? So I call dL1. So YL, well, energy per unit time, so it's a luminosity. So using the results I showed, we derived before, I see that this is just, so taking the element, the surface element, as I told you, in such a way that it lies, it's a small tile of the spherical surface, it means that its unity vector is radial, is parallel to the radial direction because of the properties of a spherical surface. Okay? And not only that, but if you move, so for example, the flux F1, the radiative flux, what kind of direction am I expected to think for that? Well, again, because of isotropy, F1 cannot have a preferred direction, so can only be radial, just because of isotropy. So both are parallel. F1 and dA1 must be parallel because of isotropy. Well, dA because I took it as a small tile of the surface, of the spherical surface, and F1 because of isotropy. So I call just F1 here, this guy, as the flux measured at a distance R1, which is coming out radially or perpendicularly to the spherical surface. Now, look at that. If you move the surface element dA by keeping up the same spherical surface, so keeping it at a distance r1 from the source, that value, the dl, what we call dl1, is not going to change because of isotropy again. So f1, this quantity here, is a scalar which is not supposed to change as long as you stay on this surface, which I call S1, so sphere 1, okay? Because again of isotropy. So you realize that if you play this, so and then by integrating, this is an integral over dA. So if you integrate over the entire S1 surface, over the entire sphere of radius R1, of course the result, given that F1 is constant, is just the total area of the surface, of the spherical surface. So the integral over S1 is just 4 pi R1 squared, okay? Surface of the sphere. You might have noted that the result of the integral, which is a total luminosity, I didn't call L1, just called L, for the reason that I'm going to comment in a moment. So if you play the same game now, considering a different surface, a different spherical surface at a radius now R2, so for example bigger than R1, so you play the same game, and again, you infer that in this case the flux will be different. You don't know. So we call F2. But we know that whatever F2 is constant throughout all the surface S2. So when I integrate over S2, the result is just F2 times the area of the spherical surface, which is 4 pi R2 squared. Now, you might wonder, how can I know that the 2L, the two luminosities crossing S1 and crossing S2 are the same? Well, in the case of stationary source, this is something I didn't say yet. So stationary sources means that the source, the central source, is emitting energy at a constant rate. So it's not behaving in a weird way. Weird, you know the word? Okay. So it means that per unit time, the source is spreading, is just emitting the same amount of energy. So for the conservation of energy, the same amount of energy which is crossing S1 must be the same as the amount of energy crossing S2. Otherwise, if this wasn't the case, you would have that in the space volume between the two spherical surfaces, you would have that energy is either increasing or decreasing. We are in a stationary assumption. So the source is just emitting the same amount of energy per unit time. So conservation of energy requires that the same amount of energy coming out of surface S1 is to be the same as the one coming out of surface S2. So the luminosity is just the total luminosity of the source, which is the same. Doesn't depend on the distance that you consider to measure. The same amount of energy is spread. So what's the difference between the two S1 and S2? Is that in one case the same amount of energy is distributed over a surface which is different. So you should expect a flux which is different. And indeed, if you use both relations to express the flux as a function of the remaining quantities, you see that you end up with this easy formula, which is a famous one because it tells you that in the case of an isotropic source, well, that can be generalized, but in the case of an isotropic source of a given luminosity, the flux scales as 1 over squared distance squared. So while the luminosity is the same, the flux decreases proportionally to the 1 over r squared, okay? This holds as long as you are outside the radius of the source, which I here call as capital R. Let's have a look at the units of measure. Well, the flux is Hertz per unit per ergs per square centimeter per second, so energy per unit area per unit time. And indeed, luminosity is energy per unit time. You divide it by 4 pi r squared, so it gains an extra per unit area. I here use volumetric quantities if you noted that. But if you think carefully, you can play the same game with the corresponding specific quantities. So instead of flux, instead of the volumetric flux, you can use the specific flux. Instead of the volumetric luminosities, you can use the specific luminosities, and the game is exactly the same. So again, the same law, the same result holds also in the case of specific quantities. So the specific flux will be the specific luminosity over 4 pi r squared. And of course, the corresponding units of measure of the flux, of the specific flux, will be the same with an extra per unit hertz at the denominator. Okay. So I'm expecting that you get these concepts. Somehow you should be somehow familiar from other courses. But this, now we see them under a different light, in a different fashion. So you should see something somehow familiar to you, but seeing, as I said, in a different way, okay, in a different context, going through different quantities. Simple exercise that I advise you to carry out to make sure I will give you the result. So let's assume we have Sun and the Earth. Of course, this figure is not to scale, so just mind that. Let's assume that the Earth is moving along a perfectly circular orbit, which is, is not exactly, but to some extent can be approximately considered as a circle. And this distance is roughly 1.5 10 to 8 kilometers, okay? 150 million kilometers. The luminosity of the Sun, if you don't know it, I tell you, this is 3.8 10 to 33 ergs per second. So we can assume that the Sun is an isotropic source, which is quite reasonable assumption. So we wonder, the question is, what is the flux at the Earth distance? So if you could go beyond the clouds, so above the atmosphere, this is important. Why? Because a lot of energy radiated by the Sun is just reflected into space by the clouds. So just neglecting the clouds. So you imagine you go with a space rocket, you go just above the atmosphere. You measure how much radiation. So the flux, what is that? Energy per unit area per unit time. Okay. So how much energy is coming from the Sun at our distance? And also, for example, you can calculate the same quantity at Jupiter's distance. I don't give you the Jupiter distance, but I give you the revolution period of Jupiter in units of Earth year, or just year. It takes for Jupiter almost 12 years to make one full orbit, precisely 11.86. You have to figure out how to calculate it with no other information. What you need is over there, here in the slide. So make sure you can do that. This is something, for example, I could ask you to see. Very easy calculation. I'm not expecting you to carry out too hard, but this is something which you should manage to calculate. The answer to question number 1 is this one, 1.34 kilowatt per square meter. This is also very important. It's also known as the solar constant, which in ergs per square centimeter per second is also that way. Second answer is almost 50 watt per square meter. So make sure you can calculate that. If you have a problem, you let me know. Okay. So moving on. this is another very important property, which somehow might sound like counterintuitive for the reasons that we'll see in a moment. So let's set the stage. Let's comment on this figure. Let's suppose you have two surfaces, two elementary surfaces at some distance, which I call capital R. We call these two elementary surfaces dA1, dA2. And in between, there's nothing. Free space, vacuum. There's no medium, okay? There is no matter in between. Free space, vacuum. The two are facing one another. So it means that they both lie on parallel planes, or if you like, their normal vectors, unity vectors, are parallel. Okay? Let's suppose that there are some rays of light which are crossing both of them, for whatever reason you may like to think. And these rays are exactly what I've drawn here. I've drawn only the rays that are crossing both surfaces, okay? In all possible way, I don't care. The only requirement is that all the rays that I'm considering, so all the associated radiation, which is carried forward by these rays, is just has to cross both. First one and then the other one at some point. So let's express, by exploiting the definition itself of specific intensity, let's express the amount of energy which is crossing surface dA1 within a given frequency interval d nu, within a given time interval dt, and directed along a given solid angle d omega 1. So if I consider the amount of energy due to these rays, this is by definition, it follows just straightforward from the definition of I. This is just I nu 1 again, because I'm thinking of surface at point 1. I nu 1, I have to multiply by, I remind you, the intensity, the specific intensity is energy per unit surface, per unit frequency, per unit time, per unit solid angle. So you have to multiply all the corresponding intervals. So, well, the surface element we are considering is just dA1, so times dA1 within a generic frequency interval d nu, within a generic time interval dt, and d omega 1. What about d omega 1? Well, I told you at the beginning I'm considering only the rays that are crossing both surfaces. So d omega 1 is somehow connected to both surfaces. I will explain this more in detail in a minute. In a completely symmetric way, you can reason the same for the second surface. So the same amount, the amount of energy, which I call dE2, crossing the surface element dA2, is just by definition the value of intensity at that point where surface 2 lies, so which I will be supposed to call I nu 2 times dA2 times, well, the same interval, the same frequency interval, because I'm considering the same photons. So the same photons will have the same frequency. So the same frequency interval d nu, an equal time interval dt, and d omega 2. Now the question is, what are d omega 1 and d omega 2? Well, let's consider the problem from the point of view first of d omega of dA1. So we want to calculate d omega 1. Well, among all the rays crossing dA1, you cannot take all of them. You must take only those rays which will be then crossing dA2. But selecting all those rays means that you make a selection on the solid angle of all the possible rays. And what is the solid angle? The solid angle is the surface over square distance, definition of solid angle. And the surface you have in mind now, let's suppose you are standing on the point where dA1 lies, okay? So you are watching dA2. So you want to select all the rays that are crossing dA2. But from your point of view, that means you are selecting the solid angle subtended by dA2 from your point of view. And that means that d omega 1 is just the surface of d omega 2 over r squared, definition solid angle. Surface of the element, the solid angle subtended by a given surface element is just the surface area over distance squared. And you realize that now if you consider the same aspect, moving to dA2, you stand where dA2 is, so you want to select all the rays that are coming from dA1. So you are making a selection. You do not buy all of them, you just buy those coming from that direction, which means d omega 2, from your point of view, is just the solid angle subtended by dA1. And the distance is the same. Of course, this r is just the mutual distance between the two surfaces. So this is the only, I'm not going to call subtle point, but this is just the only point probably in this line of reasoning which requires some careful thinking. So I hope it's somewhat clear. If you now combine, so if you replace d omega 1 into here and d omega 2 into here, well, we need some further considerations. Well, now we selected from both point of view, the very only rays that cross both surfaces. And indeed, you expect that the same amount of energy crossing one surface will equal the amount of energy crossing also the other surface, because the very same rays are traveling in the vacuum, so nothing can affect them. So the same amount of energy, conservation of energy, that has crossed dA1 at some point will be crossing exactly within the same time interval, within the same frequency range, will be crossing dA2. So by equating the two energy, dA1 and dA2, because of energy conservation, energy cannot disappear, cannot either disappear or being created. Just you replace the two, you set the two quantities equal. You see that everything cancels out, and in the end, you are left with the two intensities. So you might say, oh, all this mess just to get to a very simple result. Yeah, very simple, but very meaningful and not so obvious. It means that intensity in something which, when a given radiation, a given amount of radiation is traveling in vacuum, intensity doesn't change along the path. Energy intensity remains the same. I will be commenting in the next slides why this may sound counterintuitive, but this property allows us to really offers us a clue to understand the meaning of intensity. So intensity is something which keeps constant along the rays, along the path, provided that the path is through free space, okay? If we put some matter in between, things may change, because matter indeed can affect radiation, which is exactly the general topic of radiative transfer. So, but in order to understand how intensity is affected by matter, you have to understand first of all, preliminarily, I would say, the behavior of intensity in the absence of matter, okay? So that you can reason, you can study and understand what happens when you put matter along the path. If you want to be, posh and say using you want to use an elegant argument, an elegant way to show this, you might have said, okay, I remember that intensity, as a matter of fact, is proportional to nu cube, so frequency, and to the distribution function. If you remember, the distribution function is the number of particles, number density in the phase space. From your previous studies of, I suppose, mechanics, you should be very familiar with the Liouville theorem, which states the conservation of this number density in phase space along the path of the particles. So if you now apply the same line of reasoning here, well, the particles are photons, they travel along the path. So given that F is constant along the path because of Liouville theorem, given that the frequency of photons doesn't change because there's nothing which can affect photons during their traveling, well, I'm also supposed that as a consequence also I has to be constant along the path. Another way to put it. So if you like, if you're very fond of Liouville theorem and more elegant, as I say, posh is a posh way, very. Either way, the important is just to reach the same conclusion. I doesn't change along the path in free space. Okay, this is an easy case, important application, which we, from some aspect, we recover the results about the flux scaling with distance that we already found. But in addition, it tells us something more. So let's assume we have a uniformly bright sphere. What does this mean? Well, it means that the intensity evaluated over all the points of the surface is the same value. So uniformly bright, that is the meaning. The same brightness across all the points on the surface of this element. Let's assume, so constant intensity through all the points of the surface, I, which I call also B, just to mean something constant. Let's suppose we want to calculate the flux at a given point, which I called P. So I put myself here, P, at a distance from the center of this star, R, where capital R is the radius of the sphere, okay? So I put myself outside of the star, outside of the object. So R has to be greater equal than capital R, okay? So in this drawing, clearly I'm outside, I'm well far from the object. I'm here, and I want to calculate the flux. Well, see, if I say calculate the flux, I have to have in mind a surface. So I take the surface, which is whose normal direction is just radial, okay? So just take a. I didn't draw here just not to make too many things here. I didn't want to mess up this drawing, but just suppose you have a surface element just perpendicular to the radial direction, okay? So my goal is I want to calculate the flux over the surface at this distance. So you see, you have to calculate, if you remember the flux, you have to integrate the intensity in that point, at that point, times cos theta, and you have to integrate over the entire sky. So let's consider, well, if you consider all the possible direction here within this cone, which here I denoted with these yellow arrows, well, you have some flux, because all these lines, if you get back, they match at some point, one point of the surface. So if you remember, the intensity along one path is constant. So if you consider this line, for example, this one here, it means that you see the intensity here is the same that you measure here along this direction. But if you consider slightly off directions with respect to this cone, if you imagine to prolong this dashed line wouldn't match any point of the surface. So in that case, I is 0. I is constant within that cone. As soon as you move off the cone, I is 0. Because if you look at that direction, your eyes do not match any point of the surface of the object. So I is that guy. I is constant within that cone and 0 outside that cone. Easy. You see that? Okay, so let's apply the formula, the definition of flux. Integral over d omega I times cos theta, where theta is what? Well, theta is the angle between the radial direction, because the way I chose my surface element, and the generic direction. So theta is this angle here, or equivalently this angle here. Okay. But okay, let's be more specific. Let's express the generic solid angle element in terms of the azimuthal angle and the polar angle. The polar angle is just theta, and the azimuthal angle, this is a problem with cylindrical symmetry, if you think. So d phi is just the azimuthal angle, and there's no dependence on phi. So you just phi get integrated between 0 and 2 pi. So, and what's the boundaries of the integral over the polar angle? Well, between 0 and what? And the angle which defines that cone, which I called theta c. You see, theta c is the boundary case, is the rays corresponding to the limiting cone. So this is theta c. You cannot go beyond theta c. Beyond theta c, I is 0. Okay. So working out this integral, well, you gain a factor of 2 pi from this integral here, and integral of sine theta cos theta, easy task, also for the guys in the other room, is just 1/2 sine squared, calculated between theta c and 0. But what is sine theta c? Let's have a look at the figure. Sine theta c, by definition, if you want, of sine, is just, let's consider this triangle, P, the center of the object, and this point. So this triangle here, sine of theta c is just this guy, capital R, over this guy, small r. So sine theta c is just capital R over R, just like that. So this guy is just R over R squared, because sine squared. So pi b, I remind you, is I, is the value of I, which I took out of the integral immediately because I is constant within that domain. And so you immediately see two things. One thing is the one I wrote here, which again, the flux scales as 1 over R squared. So the further you go, the lower the flux you measure, which somehow is also something which matches your everyday experience. The further you are from a source of radiation, the fainter the flux you measure. And how? What's the scaling? 1 over R squared. That's exactly what we saw before. Now we recovered in this case in a different way. The interesting thing here, in addition, is that you can calculate, for example, the flux exactly at the surface. You see, I didn't make any assumption on the value of R. The only constraint is that R is greater or equal than capital R. If you move P, so if you go right on the surface of the object, all what we did here still holds. So in particular, if you replace the value of R equal to capital R, so you go on the surface, you move to the surface of the object, you can express, you see, the flux as a function of intensity. And there's a pi. So the flux of a uniform Blériot sphere on the surface of the object itself is just the intensity itself, B, times pi. This is an easy, handy relation, handy formula, handy result, where we will be exploiting several times in the following, few times. You might also make some considerations, dimensional-based consideration. So, for example, let's have a look here. I'm still looking at the bottom one and the bottom equation here. The flux is, for example, here you see something that I didn't say yet. I didn't specify whether I was thinking of specific flux or volumetric flux. You can assume both cases, and the same will be the argument will be the same. If you assume specific quantities, here I should have written I nu instead of I, B nu instead of I, and F nu instead of F. But the same argument works exactly the same way, or just volumetric, as my notation would let you think. Having written just I, one is led to think, well, this is just total intensity, no more specific volumetric intensity, and the flux might be. Let's assume, for example, they are in specific quantities. So if B here is B nu and F is F nu, B nu is an specific intensity. So it's energy per unit area, per unit time, per unit frequency, per unit solid angle. Times pi, you have flux, specific flux, which is the same except for per unit solid angle. Pi works like a multiplication, a product by a solid angle. Multiplying intensity or specific intensity B times pi is like it's kind of multiplying by a solid angle. And pi is not by chance, dealing with solid angles. But this is a special case in which intensity is constant. Okay. So whenever you have a uniformly bright object, you know intensity on the surface, and you want to know the flux at that point, just a matter of multiplied by pi, or the other way around. If you know the flux, you want to know the intensity of a uniformly bright object, that divide by pi. It may sound a little bit complicated, but it's not. When you have to apply it, then it's a matter of fact. As a matter of fact, it's easier than you might think. A few considerations, going back to the difference between flux and intensity. So, for example, let's suppose you have a source with a given specific flux, and the solid angle subtended, from your point of view, subtended by the source is just omega. So you can work out, let's assume constant quantities, so just the intensity or the flux is just I times the total solid angle omega. So you can express the intensity as the specific flux over the solid angle. Well, the specific flux is the formula we saw a few slides before. So the flux is energy per unit time, so luminosity, over distance, so 4 pi d squared, if d is the distance between the source and you. This is specific, so you also have to divide by the frequency interval, delta nu. Delta nu is the frequency interval. So this is the specific flux that you are expecting to measure from a source which is lying at a distance d from you and which is emitting energy with a luminosity L within a frequency interval delta mu. Well, you see, let's suppose that the same source, you can think of a practical example in this case. Let's suppose that the same amount of energy per unit time, per unit frequency is spread over, in two different cases, over two different solid angles. So you can think, for example, of a lamp, a light bulb, a lamp, in which in one case has a given size, so a small size here on the left. In the other case, you take your lamp and you put some kind of soft light globe, something which spreads the light over a larger volume. So if you look at the source in both cases, you see the same amount of energy because the lamp is the same. But in one case, you have the same amount of energy, which is spread over a larger volume. So it means that the solid angle subtended, you are at the same distance in the two cases. So the solid angle subtended by the source in the right panel is larger. So the same flux, look at the formula of the specific flux, luminosity over distance delta nu. These quantities are the same in these two examples, same quantity. You are the same distance from the two objects. The two objects have the same luminosity. They are emitting in the same frequency range, equal everything. The only thing which is different is the volume. In one case, you may think that the luminosity, the energy is spread over a larger volume. So you see the object bigger. Bigger means that since they both lie at the same distance, the bigger one will subtend a bigger solid angle. So let's have a look at the formula of I. You have the same flux over different solid angle. So you have same flux, different intensities. And what is the result? Well, the result is indeed that the object having the smaller solid angle appears to be brighter. And this is, everyone knows. If you have a very bright source of light in your room and you want to soften it, you just spread its light. You just put something, just make sure that the solid angle subtended by the source, probably the layman wouldn't say that. We are physicists, so we use a more rigorous language, but the action is the same. You spread the luminosity, the flux in particular, over a larger solid angle. So the intensity decreases. And you perceive it as less bright. So what does this mean? That your eyes are sensitive, rather than to flux, are sensitive to intensity. Because the flux is the same here. But you are, if you wanted to decrease the brightness of the object, you use the trick of increasing the solid angle. So the same amount of energy coming now from a larger solid angle. So F nu over omega is smaller. So you feel better, less bright. So your eyes, your vision, human vision, is sensitive to intensity. Now, if you think of the result that I showed you before, that intensity is constant along the path in free space, this might surprise you. Again, let's move on this with this kind of considerations. So the difference between intensity, flux, of course, is intensity does depend on. If you fix the point in space, intensity can change. If you change direction, the flux is just the flux. Well, if you consider a different surface, if you change orientation of the surface you are considering for the flux, of course, the flux changes as a consequence. Indeed, unlike the flux, which we saw scales with 1 over r squared, so that's why the further the source of light, the less flux. The smaller the flux is 1 over r squared, where r is the distance. Intensity doesn't work like that. Intensity is independent of distance. And you can appreciate this again. Well, we already know, we already proved it, but you can have a more intuitive grasp of it if you consider, again, this ratio between the specific flux and omega. Omega is the solid angle subtended by the source. Why? Well, the flux, we repeatedly said that the flux scales as 1 over d squared. That's exactly the formula I already used. But if you think, if you have a given source of radiation and you put it further and further from you, well, of course, the flux scales as 1 over d squared. So the flux decreases. So the numerator decreases. But also the subtended angle, the angle subtended by the source. The further you move, the smaller it gets. And how much? Well, definition of solid angle is just area A, area the projected area of the source, which is constant as long as you keep the same object, over d squared. So you see that they behave the same way. Both numerator, flux density here, and denominator, solid angle, they both scale with distance in the same way, 1 over square distance. So understandably, their ratio doesn't depend on distance, which is exactly the reason why specific intensity or brightness doesn't depend on distance, because it's the ratio between two things which scale the same way with distance. So if I look at the sun, so let's suppose I'm living now on Mercury. We are living on Mercury, which is really a good place to live on. So the sun, the flux coming from the sun is incredibly large, much larger than the solar constant. And you could tell me how much. If I move to Earth, to Venus, to Earth, to Mars, the flux scales down, but also the angular size of the sun scales down accordingly, the same way. So their ratio remains the same. So it means that the intensity as measured at the Earth distance or from Mars is exactly the same. But remember that intensity is what your eyes are sensitive to. So what does this mean? You know that looking directly at the sun is not a very good idea, particularly if you do it for too long, because your photoreceptors can be damaged, and are for sure damaged if you look. I don't know how long to have permanent damages, but not too long. So it means that given that your vision works on the measure of intensity and not the flux, it means that if you look straight at the sun for the same amount of time, when you are on Mars, Mars is a distance of about, well, I would say, let's say 250, 220 million kilometers rather than 150 million. So if you look at the sun directly from Mars, you risk the same kind of damage. And now you might wonder, so why, when I'm looking at the stars, well, the stars have the same intensity of a given star doesn't decrease. So I should be supposed to have the same damage when I look at the sun, which is of course not. I can look at the stars for an entire night without any damage. In that case, the explanation is because the angular size of the star is so small that is much smaller than the angle subtended by one single photoreceptor of your eyes. So that's the limit. And so as a matter of fact, the intensity of a star is exactly the same intensity that you have at the surface of the star. Exactly the same. The intensity doesn't change. But the energy spread by the rays of light coming from a star is coming from a solid angle which is so small that is spread over a larger solid angle, much larger. And what is this larger solid angle? The area of one single photoreceptor of your eye. So it's just because of that. But so if in the future you will be fortunate enough to go to Mars, which I don't believe, because you are too old, probably you're in 2-3 generations, I don't know. But let's suppose you can travel to Mars. Do not look straight at the sun. This is a bad idea. This is nice. So this immediately, the first time you hear this, you might perceive it something, as I said, counterintuitive. And it is to some extent, because you think your eyes works based on the flux. But indeed, it works with intensity, not with flux, with the limit of the angular size of the photoreceptor that I was mentioning, of course. Think about it. You have to think about it on your own. So, okay, this sentence just summarizes what I've been repeating for a while. So, intensity is exactly property coming straight from the surface of the bright object. unless it is affected by the presence of matter which lies in between along the path. But this is a different story. So let's see another example just to get acquainted with these quantities. So I read this example. A radio source at a distance of 20 megaparsec is observed with a telescope with a collecting area of 300 square meter at a frequency of 22.2 gigahertz with a bandwidth of 250 kilohertz. The source is determined to have a flux density of 20 Jansky and is found to be a uniform circle with an angular diameter of 30 arcseconds. So we have three questions. Let's see one at a time. So what's the intensity at that frequency? So to figure out, okay, let's summarize. We have a source, we know the distance. You should be already familiar from the course of previous classes of what a parsec is. So megaparsec is just 10 to 6. Is observed with a telescope with collecting area. So you have the area of the collecting telescope. You have both the central frequency and the bandwidth. So if you remember the previous example, what matters to us is just the bandwidth in this case, rather than the central value. So 250 kilohertz. You have the flux density, 20 Jansky, so energy per unit area, per unit time, per unit hertz. And you know also the size. So the solid angle, you have you don't have the value, but you have all the ingredients, all the values needed to work out the solid angle, because you know the angular diameter in arc seconds. So the intensity of that frequency, what is that? Well, first of all, you have to calculate, as I said, the angular size of the source. So the solid angle. And what is that? Well, let's call omega. You have the diameter, the angular diameter. So just work out the radius. So 15 arc seconds. And you have to express it in radians if you want the result to be expressed in steradians. So what lies among brackets is just the radius of the circle in units of radiant. You remember the telephone number, all the astronomers call it telephone number. The one at the denominator, 206265, is the number of arc seconds within 1 radiant. Okay, so having radians and wanting that in radians, you have to divide by the number of, by that telephone number. Pi, yes, because you are calculating the area of a circle. So pi radius squared, just like that. Okay, so you calculate the radius in radians, pi, and then, given that this is small, this is because it's a small circle, okay. So this is just the result in steradian. And now, well, easy. You have the power. You have the specific flux. So again, I put among brackets. Jansky means watt per square meter per hertz, and this is the conversion between Jansky and international system units. Over watt? Well, you just miss the angular size. So divided by the angular size of the source. I'm just going slowly, just to make sure, as I said, to be in control of the units of measure. So you find that this is just watt per square meter per hertz per steradian, which is exactly the unit of measure that you would expect for an intensity, just like that. Second question, what is the total power of the radiation detected by the telescope? Well, the total power has to do with, of course, the collecting area. And in particular, what is that? Well, you want the total, you want power, so energy per unit time. So you want to consider all the frequency range, which is collecting, through which the telescope is collecting radiation, as well as the area. You calculate it. You have the specific flux, so energy, the area per frequency, per time, per unit time. So you multiply just by the collecting area and by the frequency range. And so you are left with energy per unit time. So the total power collected by the telescope. So again, F nu, the specific intensity, you see from the units of measure that when you calculate, when you multiply by the area, you get rid of this. When you multiply by the bandwidth, you get rid of this. So you're left with watts, I should say. So again, this first term among brackets is just the conversion between Jansky and International System units. This is just the area of the collecting area of a telescope. This is the bandwidth in Hertz. So 1.5, 10 to minus 17 watts. And this is the total power. Finally, what is the luminosity of the source over the observed spectral range, assuming that the radiation is isotropic? Well, in that case, specific flux times what? Well, again, times frequency range. But in particular, you are at a distance d of the source. So either you take the formula like we saw before, or if you want to reason here, well, you observer lie at a distance d from the source. So you are lying on a spherical surface of radius d. So calculating the entire luminosity means multiplying the flux that you measure times the total surface, total spherical surface of the sphere onto which you lie, you observer lie. It's a sphere with a radius d. This is the distance between source and observer. So 4 pi d. Again, you can express F nu delta nu this is just what we saw before as the total power over the collecting area. So replacing that, all the values, again, make sure you are in control of the units. I remind you, 1 parsec is 3.1 10 to 18 centimeter or 10 to 16 meter in this case. I remind you also the meaning of parsec. Parsec is the distance at which an astronomical unit, so 150 million kilometers, subtends an angle of just 1 arc second. The annual parallactic angle is just 1 arc second, if you want to use a more rigorous language, which is 10 to 0.4, 10 to 19, 29 watts, or 10 to 36 hertz per second. Okay, any questions so far? Okay, I'll go on for, I would say, at least 20 minutes, more or less. I let you have fun, so as to speak, with this exercise, for which I will provide you the results. I'm not gonna give you right now. So let's read the text of this exercise. An alien civilization at a distance of 7 parsecs uses a radio antenna of diameter 100 meters as a transmitter to beam a radio signal toward Earth. The civilization converts 5×10⁶ joule into this signal, which is then transmitted at a constant power for 100 seconds, centered at a frequency of 1 gigahertz with a bandwidth of 1 megahertz, and in a beam with a solid angle of 9.3 10 to minus 6 steradian. So what is the luminosity of the beamed signal? What is the intensity of the beam signal? And then it adds, the signal is detected with an antenna of diameter 7 meters at a frequency of 1 gigahertz with a bandwidth of 500 kilohertz. What is the measured flux density of the signal, and what is the measured power of the signal at Earth? Have fun. At some point, I will share the results. I'm not querying you. I'm not. It's just for you. It's useful to make sure you're getting familiar with these quantities. Okay, so now let's review the elementary processes taking place on an atomic level, which are responsible, thanks to which matter can either emit or absorb radiation. And let's characterize them and see how we can encode using the previously defined quantities. So let's start with spontaneous emission. What is that? Well, we know that matter has the property of emitting radiation in a spontaneous way. Spontaneous means that it is independent of what's going on in the environment in which matter lies. Why this? Well, because of the atomic nature of transitions. At some point, one atom, with all the configuration of the electrons, some electrons can change level, orbital. And by doing that, of course, you know that there is either, in this case, the emission of a photon with a given frequency, whose frequency corresponds to the difference of energy between the two levels, between the initial and the final level of the electron that has moved, okay? And this happens just because of the nature of matter. So this process is spontaneous in the sense that it just occurs because of the nature of atoms. Of course, it depends on what kind of atom, what kind of matter, in which state, physical state, with temperature, a lot of things, but it's independent of the environment. So either it doesn't depend on whether I put that matter, that gas, in an environment filled up with an intense radiation field or no radiation field at all. It's independent. So it's independent of the radiation field, okay? Spontaneous emission in that sense. You've got that atoms and at that temperature, that ionization level, whatever, at that point you would expect some emission, some spontaneous emission, which doesn't depend on the radiation field, on the environment of the. So how can we quantitatively define this, characterize this spontaneous emission? Well, you would expect that you have the production of energy, of radiation, somehow per unit volume and per unit time, and also, if you care about the direction of the radiation, also per unit solid angle. So we define a quantity which is J, so-called spontaneous emission coefficient, which is just, look at here on the left, J is the amount of energy emitted through spontaneous emission per unit volume, dV, per unit time, dt, and emitted per unit solid angle, so within d omega. So as a consequence, the amount of energy is by definition of J is just J dV d omega dt. J specific, spontaneous emission coefficient is just energy per unit volume, per unit time, per unit solid angle. You can define the corresponding specific quantity. So, and we call J nu. Of course, it's specific, so you have to explicitly show the dependence on frequency. And if you compare to the previous one, you just gain an extra factor of d nu, given that now the specific spontaneous emission coefficient is defined per unit frequency. In order to have dE, you have to multiply also by d nu. Otherwise, it's exactly the same. dV, d omega, dt, d nu. You see, all these quantities that we've been introducing are not difficult to understand, but they are, well, you have to pay attention because you have many. They are defined per unit of many things. So just make sure. You can also define if you integrate, if you don't care about the direction of the produced radiation, just care about the amount of radiation produced per unit volume, per unit time, you can define the specific power. So the specific power is just the integral of the specific spontaneous emission coefficient over the entire direction, over the entire sky. So it's just the integral in d omega of J nu, just like that. Specific power. Specific power. Why? Energy per unit time. So it's a power. It depends on frequency. So in order to have power, you have to multiply by d nu. And mind that this case is also per unit volume. If you consider the special case of an isotropic field, again, so spontaneous emission is producing radiation with the same amount of radiation spreading, moving towards all directions in the same way, so isotropic case. So you can define, you see that integral, the specific power, given that this guy doesn't depend on the solid angle, this is just 4 pi J nu. So in that case, you can define, knowing the specific power, you can express the specific coefficient as the total power, the specific power over 4 pi, just like that. We can also define a new quantity, which is so-called the emissivity, which I call epsilon nu. The emissivity is the amount of energy produced per unit mass, instead of per unit volume, in this case, per unit mass, per unit time, per unit frequency. So I say it again. The emissivity is the amount of energy emitted. Again, of course, we are talking about spontaneous emission. So emitted by spontaneous emission per unit mass, per unit time, per unit frequency. You might have noticed that I didn't say per unit solid angle. I didn't. But if you want to find the relation between emissivity and J nu, so we conveniently express the same amount of energy that we meant here. Here we meant by dE, we denoted a given amount of energy produced in the volume dV, in the time interval dt, in the frequency interval d nu, within a solid angle d omega. Now, if we want to express the very same amount of energy in terms of emissivity, okay, emissivity multiplying by the amount of mass that you have in dV is just rho dV, where rho is the mass density. Why this? Because emissivity by definition is per unit mass. So we have in mind the energy produced by the volume dV, so you have to work out how much mass you have in dV, rho dV. So emissivity times rho dV times dt times d nu. You want only, from the previous case, from this dE, you are taking all just the rays along d omega. But given that the emissivity by definition takes everything, and you want to select only d omega, you have to select the fraction. And the fraction is d omega over the entire sky. So the fraction is d omega over 4 pi. Because you want this dE to be equal to this dE, okay? And in this dE, you select just d omega. So you have to select, in this case, the fraction of all the photons created that are directed along this d omega. And the fraction is d omega over the total. The total is 4 pi. And so you combining the two, by equating the two, you see that J nu can be expressed as a function of the emissivity and the density, and the matter density, the gas density, inevitably, because emissivity is defined per unit mass. So it's just the emissivity times rho over 4 pi. 4 pi just reminds you that one of the two guys, I mean, on one side, J nu, and on the other side the emissivity. One is defined per unit solid angle, the other is not. So 4 pi just is reminiscent of that. I remind you that the quantity that we've been using to describe the properties of a radiation field is intensity, brightness, okay? Specific intensity, brightness. So what's the impact? How does the spontaneous emission that we define through this coefficient, how does this guy affect the brightness? To understand that, let's consider a cylinder along the path that we've been considering of the radiation. So in particular, let's consider a surface element dA, and the cylinder has a path length here of ds, we call ds. We wonder now, let's assume that the intensity here, corresponding where dA lies here, we call it I nu. We wonder now, what's the value of I nu on the other side of the cylinder, here? So in general will be I nu plus d I nu. So the variation, the change of the, which we have no idea what it is that. And in particular, let's consider all the photons that are moving along this path within the solid angle d omega. Okay, we're not just taking all of them, just all those traveling within the solid angle d omega. So we wonder, how much do we gain thanks to this volume because of spontaneous emission? How much energy do we gain from moving from here to here? Why do we gain energy? Well, we gain energy because within that volume, atoms contribute to radiation thanks to the spontaneous emission. So the amount of energy that we gain, we can express in terms of, as a function of J nu. But J nu, I remind you, is the amount of energy per unit volume, per unit time interval, per unit frequency, per unit solid angle. So we have to multiply J nu times what? Well, that corresponding volume. And the volume is just dA times ds, the one I put among brackets. So that gives us the volume, and then dt, d omega, d nu. That's indeed, by definition of J nu, that's the amount of energy which is produced within that volume, produced by spontaneous emission. You see? So I call this dE. This is the amount of energy that I gained. But this amount of energy is just what I gained. What I didn't have here at the beginning and what I have here at the end. So it is the amount of energy which has increased, which has contributed to increase what I already had at the beginning of the cylinder. So this is exactly something which I can express as a function of the change of the brightness. So the brightness has changed in such a way that now I have more energy crossing the surface, the final surface. And if you think of the definition of intensity or brightness, this is energy per unit surface, per unit time, frequency, solid angle. So I have to multiply this guy here. So the brightness increment times surface, time interval, frequency interval, solid angle interval, which are the same. And so you immediately see that the increase experienced by intensity is just the specific intensity, the specific spontaneous emission coefficient times the length of the path. The longer the path you consider, the correspondingly higher the increase in the intensity. And if you think carefully, that makes sense. The longer the path, the more the gas contributes with spontaneous emission along the path itself. So in the end, at the end of the path, you will have gained correspondingly more energy because you crossed a correspondingly longer path along which spontaneous emission contributed. It's also worth paying attention to the units of measure. You see, I is energy, so DI is energy per unit surface, blah, blah, blah. J is energy per unit volume, and the same blah, blah, blah. So to move from J, which is energy per unit volume, to energy per unit surface, you have to multiply by a length, which is exactly ds. So this helps also to figure out exactly dimensional analysis is helpful also in this. Okay, last one for today's class is we saw something, spontaneous emission, which contributes to increase the radiation field. Let's see now the opposite, absorption. We also know for the very same mechanisms that photons can be absorbed by atoms, particularly when they match the difference in energy between two levels. So you can move an electron from one lower level to a higher energetic level by letting the atom absorb the photon. So as a matter of fact, the same gas, the same matter, can also absorb photons. So can decrease intensity. Let's figure out how this works. Again, let's consider a generic cylinder which is crossed by the radiation. I tell you that the decrease of intensity, which I call again di nu, of course this is a decrease, so the change is negative. So that explains the minus sign. And then there is, it's proportional to ds. The longer and the more absorbing atoms the radiation will encounter, will come across with. And also there's a coefficient, which is alpha nu, which is length minus 1. In a moment, I will prove where this comes from. What is the meaning of this drawing? Well, you have to think that the capability of matter of absorbing radiation is due to the single atoms. So you have to figure out, you have to visualize and this is the idea behind this figure, the single atoms as tiny sources of absorption of radiation. So the more you have of them, the more capable the gas is to absorb. Not only that, but you also have to characterize the capability of an individual atom to absorb radiation. And you can quantify it, you can express it with the so-called cross-section, you know already. So the higher the cross-section, the higher the ability of a single atom to absorb radiation. In particular, you can think of a geometrical meaning of this cross-section. So you can wonder, okay, how many particles, atoms, I have in that volume? Well, if we call with n the number density, so number of atoms per unit volume, so the total number is just the number density times the volume. And the volume is the same guy as before. Surface dA times ds. So dA ds is just the volume, n is the number density. So n dA ds is just the total number of particles, total number of atoms that absorb radiation within that volume. So you can, how much radiation will be absorbed? Well, you can think of the total projected area, dA, that's the total area through which radiation flows, and what's the fraction of that area that will absorb radiation? Well, that's the total projected area of all your atoms. Given that the projected area of one atom is the cross-section that we called sigma nu, so sigma nu is the cross-section, the area of one single atom. If you multiply by all the number of atoms, you have the total shadow. It's a kind of shadow, cast. It's a shadow which is cast perpendicularly to the to the direction of motion of the radiation. And so, just multiply the area of one single atom times the total number of atoms. So you have the total area which is shaded. So whenever a ray of light goes through and doesn't match any of these atoms, just goes through. Whenever it matches one of them, it belongs to this fraction of area. So you can assume that the total number, the amount of radiation will be just the total radiation times this fraction. The fraction of area which is shadowed by all these absorbing atoms. So on one side, you just, as we did before, the very same. In this case, we have this minus sign because we know that di is negative. So we want here something positive. So minus di, dA, d omega, dt, d nu is the total amount of energy which gets lost, gets absorbed. Okay, so di is negative, we want here something positive, minus di. So this is the quantity that gets lost, get absorbed. But this is the fraction, the very fraction of the incoming of the energy which is entering, which is I d omega dt d nu, times the absorbing area. Okay, so in that case, instead of dA, we have to put the total shadowed area, let me say this way. So the area which, the kind of shadow which is cast by all these absorbing elements, which is exactly the quantity here. So instead of the area, here you have to put the fraction of that area, which is shadowed. And indeed, you come up with what I showed you before. You see that indeed the loss of radiation, so the loss of intensity, is proportional to the intensity itself, of course. Because for the same amount of atoms, if you double the intensity, well, each atom will absorb twice as much. So the amount of absorbed radiation scales proportionally to the radiation itself. And this is indeed what we found here and what I already foretold you here. Then ds, and then you immediately see that what here we call this absorption coefficient, I probably didn't mention explicitly, but alpha nu, which has the size of length to -1, is so-called absorption coefficient. And you see from here, if you compare with this relation, you see that the absorption coefficient is just the number density times the cross-section. If you work out, if you check the dimensional analysis, n is length to -3, number density, number over cube volume, times sigma is an area, so 1 over length. And indeed, alpha is 1 over length. In the literature, particularly in astrophysics, people often, instead of using the absorption coefficient as a product of n times sigma, they use also as a product of new quantity. Well, rho is the mass density, and kappa nu, kappa is the Greek K, okay? It's not just K, it's a Greek K. Greek K is said to be kappa, like almost like an Italian. So kappa nu is alpha nu over rho. And it is called mass absorption coefficient, or just opacity. So when if you pick up a paper, scientific paper, talking about these topics today, this parameter will be referred to as opacity, just opacity. And what is that? Well, this is just the absorption coefficient per unit mass, essentially. More precisely, if you work out the dimension analysis of kappa, kappa is just an area over mass. So it's a cross-section per unit mass, sorry. It's not an absorption coefficient per unit mass, it's a cross-section per unit mass. It's an area per unit mass. So, while the cross-section is the kind of area per unit absorbing element, so per unit atom, the opacity is the cross-section per unit mass. So there's the density in between. Okay, I think I have to stop here because I already took my time. So on Wednesday, we keep on. You already have the PDF of the presentation, so you are welcome at any time to ask questions. Yes, please.
If you said it, I didn't read it, and I'm sorry. But spontaneous emission only depends on temperature, on the temperature of the body, and doesn't account for any type of other emissions like nuclear decay or processes going on in the matter itself?
Well, it depends on, as I said, on the physical conditions that affect spontaneous emission. So, well, that's not an answer. That, for example, temperature, ionization state, so all the reactions that matter can go through and can have as a result the emission of a photon, whatever photon. So all the possible reactions that you said that are not affected by the environment of the radiation. So if I change the radiation field in which the atom live, that process should remain unaffected. If that's the case, that goes into the spontaneous emission coefficient, indeed.
So all the photons that come out of matter.
Nuclear decay, yes, absolutely, absolutely. If you take radioactive elements, absolutely, absolutely, yes. Radioactive decay is part of the, whenever this is the case, is part of the spontaneous emission, absolutely, yes. There's a fair example of that, for example, for people who study explosions of supernovae, which is something I will be dealing with in the multi-messenger astrophysics course. For example, you have the creation, within a few minutes, you have the creation of huge amount of radioactive elements. Nickel, all the nickel 56 and all stuff like that. And the nuclear decay of this element is what powers the optical light curve of the supernova for weeks and months. And all this is studied through the spontaneous emission. All this is encoded into yes. Any other questions? Also from you guys remotely connected. Okay, so we gather on Wednesday.